go to the next presentation is from Mogens Weel on high temperature heat pump test results and further development of a high speed centrifugal compressor for steam production. Mogens is the CEO, let's say, from his own company. He's a partner from Weel Sandvig. His education is a Bachelor in Science in Technical University in Denmark in 1981. So he has been working in different areas, so process optimization of industrial and power plant processes, development of dynamic simulators for waste to energy power plants, and development of predictive emission monitoring systems for gas turbines and engines and boilers. And most recently, the development of a high temperature heat pump using water vapor. So Mogens, so please start your presentation.
Yeah, okay. Thank you. Thank you for the introduction. And it's a pleasure to be a part of this webinar with so many professional attendants. Yes, I would talk a little bit about our work with high temperature heat pumps and development of high-speed centrifugal compressors for steam generation. The major motivation for us is, of course, a phase out of fossil fuel to prevent excess greenhouse gases and global warming, but also to replace the fossil fuel in a thermodynamic and cost-effective manner using high temperature heat pump powered by electricity from renewables as wind and sun, hydro, etc. Heat pumps has very high efficiency compared to other power-to-X technologies. So I think that heat pump is a little bit unlocked in the discussions. If we compare the efficiency for different kind of systems, if we use power to heat, so we have about 95% efficiency. Power to thermodynamic, as of using heat pumps, we have 200 to maybe 10,000 or 1% efficiency. For instance, we use power to hydrogen, so the efficiency will be about 65%. Power to ammonia, 60%, or power to methanol, about 50%. Our company, we have called VSI Turbo. This is a joint venture between Weel Sandvig and Energy in Sweden. VSI Turbo has joined forces, has more than 40 years experience in designing and manufacturing of high-speed micro-gas turbines, turbo compressors, and industrial process knowledge. We are using water, and why are we using that? The major benefit is, of course, water, as we already have heard in the prior presentation, has no flammability, no greenhouse or ozone effect, no health effect or environmental concerns. It has a high COP. You could see that on the curve at the right side, where we have assumed here evaporation temperature about 85 degrees. And on the x-axis, we have the condensation temperature. And the red curve here, that is water vapor. And all the others is the other refrigerants. And as you could see here, water vapor would outperform all others refrigerants. Water can generate steam. That's obviously that if you use steam in the compressor, it is very easy just to deliver steam to the system. This has high temperature capability, about 200 degrees, low pressures, relatively low, well known in all industry, and it costs nothing. There is, of course, also some drawbacks. The major drawback is the high volume suction flow. And if you use dynamic compressors, as we do, we need very high tip speed, about 530 meters per second, to achieve a temperature lift of 30 degrees. And of course, there's no temperature light in this case. If you look at VSI Turbo technologies, so the joint venture between Weel and Sandvig and Negative. Our mission is to develop high-speed compressor technology for high-temperature heat pumps or MVR application with sink temperature from 100 to 108 degrees and heat effect between 600 to 1800 kilowatt per unit. And typically used in industrial application, that would be a distillation plant, evaporation plant, drying, and of course steam generation. So far we have been founded from the Danish government, where we have about 1 million euros to develop a compact gearless compressor for MVR or heat pump application with water vapor as working medium. In this case, we use high-speed motor and bearing technology derived from microgas turbine with already demonstrated high reliability, more than 5 million accumulated fleet hours, and 30,000 hours between major or run. And then, of course, to demonstrate the technology in the laboratory environment. And the project partners is Weel Sandvig, D2, and Egati. We have a new project now going on where we call it Powerless, where we also have a big grant from the Danish government, where we have to demonstrate the heat pump technology on a real industrial plant where they make biogas upgrading plant. You can see here there is some display from the first prototype under construction and finish. It is work as a gas loop. The compressor itself is put into this enclosure here, and the gas loop is what you can see here. That is used for about 6 meters of pipe to desuperheat the hot water vapors when they are compressed in the compressor. The compressor itself, as I mentioned before, it is a direct drive compressor with a 100 kilowatt motor. The motor has nearly the same size as a 2 kilowatt normal motor, and it has a speed about 70,000 RPM. So yeah, it's very compact system. The result here I show here for what was the isentropic efficiency or the compressor map. You can see here in this case we have the steam flow on the x-axis and the pressure ratio on the y-axis, and as we could see, we achieved a pressure ratio about 2.2, and the efficiency was about 73% here in this yellow area here, as we could see here. The expected efficiency was about isentropic efficiency was about 78%. The reason for that was primarily because we have ROPS in the initial test of the compressor, so we have to increase the tip clearance a little bit, and so that gives a good meaning that we, in that case, lose about 5%, have a 5% penalty. We have so far run it for about 200 hours and with about 50 starts. There's been no damage to the impeller so far, and we have no erosion from water droplets. Demonstrated steam outlet pressure is up to 2.9 bar, which correspond to a saturation temperature about 132 degrees. We have, of course, during initial tests, problems with evaporation and have really served ROPS. The main reason was that we have very undamped evaporation at critical speed, but the solution was to increase the tip clearance on the prototype and change the diameter of the balance piston, and then very fast pass the critical speed. But at speed about 60,000 RPM, which are where the normal operation range, the evaporation is very, very low. Also, parasitic losses was investigated. We could see we have about 18% at 60% power of parasitic losses, and we hope we can decrease that to about 12 to 14%. So you could just see here the distribution of the parasitic losses in the system. We are still working through the system where we have changed the system to what we call a closed cycle heat pump. As you can see here at the right side, we have the condenser on the top and the evaporator on the bottom. So we could test it as a closed cycle heat pump. And that is, of course, to give some learning from that, and have more practical experience with operation with small or maybe no superheat on the suction steam. Test run, they are already started. We have already done the first test run. We also make design studies of a compressor family to meet suction flow from 0.2 cubic meter per second to 3 cubic meter per second, still with constraints with a motor running 70,000 RPM and about 100 kilowatt in shaft power. And also design bearing and sealing and improved axial thrust balance system to meet a discharge pressure of about 10 bar. And of course also to reduce parasitic losses. We in that situation we also make some dynamic simulation of the system, and I would not go into detail with this one, but if you look at the left side here, you could see the path in the compressor map when we, for instance, change speed from 100% speed to 60% speed. And what we could see there is that, for instance, on this red curve here, that we have a small increase in the suction pressure. And when we have this increase in suction pressure, there could be a problem with water condensation in the inlet to the compressor, which of course there would be a risk for have water slugs into the compressor and then destroy the compressor. So we are looking into this kind of situations. As I mentioned, we are working with the design of a family of new compressors, all for a 100 kilowatt unit, and we expect to have a 1 and 2 stage and 3 stage application with possible temperature lift from in 1 stage about 30 degrees and in 3 stages up to about 80 degrees. And if you have, for instance, a 2-stage application, then we have two compressors with each with its own motor, as you could see on the picture here, and the compressor bundle itself here with the motor and the compressor inside, and the wallet is seen on this picture here. The new family of compressor, you could imagine how they look here, where we have the first one here at the left side, where we have a very high suction volume, about 3 cubic meter per second. That is when we have low pressures, about 0.2 bar steam pressure. That is the same as a suction temperature about 60 degrees. And then if we have more states then of course the suction volume will decrease, but also if you imagine the difference in the impeller shapes here, so we have this very high flow impeller on the first one, and the last impeller here where we have a inlet pressure about 5 bar would be very narrow, and you could see then that's a side view, and we have a front view of the different impellers shown here in this case here. The result from the theoretical analysis can we see here. I plotted into this diagram where many others have plotted the result in here, The blue one here is for what we call 1D mean-line analysis, and the red ones here is from CFD analysis. And as we could see here, the very low flow, that was the very narrow impeller. So we actually have a very promising design. And the mid-flow impellers, as here, we are on the line for what we could expect. The very high flow impellers, we are outside the normal design, and that we actually have a lower efficiency, and that is mainly because we have structural constraints. So we have to compromise with the design of the impeller in this case here. Also the volute geometries, we could just see them here on the picture below here. Also, mechanical stress and deformation and clearance have been investigated here from these impellers. We could see here the mechanical stress analysis, and in this case we have a maximum stress about 500 megapascal, and the allowable stress is about 808 megapascal. So we are far below what the stress limit are for this titanium impeller here. Also, deformation is a critical issue when we design the system. So we have some deformation in both the x-axial and the y direction, and we have to be sure that we not will have rubs, and at the same time we need a small clearance as possible. The next steps is, of course, that the new prototype will be built and tested here in 2024. We have to further optimize the compressor aerodynamic to increase aerodynamic efficiency for what we call stage 1, 2, and 4. And final design of a compressor heat pump unit for demonstration of nature energy plant. There the installation is planned to take place in the start of 2025. Yeah, I think that's what I have. Thank you for your attention now.
Thank you very much, Mogens, for this very nice presentation of your activities in steam compressors in your company.